Thank you for being here. Welcome. Warm welcome. Get yourself ready. Lock in with a notebook, a pencil, or a pen. Anything you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today we have this nice rocket problem from 2006. Rockets, of course, they move with a velocity. So here we have a table giving values of the velocity. And this is pretty much a integrals and Riemann approximation type problem. So give yourself a moment to try this on your own, maybe about 12 or 15 minutes, and then when you're ready, join back. And you can see how I went about this. Might be a slightly different way you went about it, that's okay. Alright, let's take a look. Here we have a table. This is velocity in feet per second. And the rocket has positive velocity after it's being launched upwards. That makes sense. And they pick up speed over time. So you'll notice that this is picking up speed. And something else that I notice, a small detail, is that it's going up by an amount that gets smaller and smaller each time. So first it's going up by 9, then 8, then 7, then 6, then 5, then 3, then 4, then 3, I can count, I swear, then 2. And these intervals are the same. So over the same amount of time, the velocity is increasing by less. That's just something to notice. Let's see, the velocity of the rocket is given for selected values above. Yeah, makes sense. All of those are equal lengths in interval time, 10 seconds each interval. So let's take a look at part A. See what they want us to do. Find the average acceleration of rocket A. Average acceleration, and do not forget to use units, indicate units, even on part B. Look at that, using correct units. Muy importante. We got to keep these units so that we don't lose points. So how do we find average acceleration? Well, acceleration is just the slope of velocity, the derivative, if you will, of velocity. So let's find out what the average is from 0 to 80. This is just going to be the velocity at 80, basically the change overall in the 80 seconds in the velocity, divided by the time. And so this is going to be, technically it's 80 seconds, and these velocities are in feet per second. So just keep that in mind when it comes to the units. That's going to be 49 minus 5, super easy. 44 over 80, which we can reduce, divide everything by 4, and we get 11 over 20 feet per second squared. That is the average acceleration. Now, like I said, it's speeding up more in the beginning. In the beginning, it has acceleration that's higher, like in the first 10 seconds. Yeah, I don't know how it's going 5 feet per second at 0 seconds. Not sure that that's possible, but anyways. So there's our units, and there's our value for the average acceleration. All right, using correct units, explain the meaning of integral from 10 to 70 v of t in terms of the rocket's flight, and then it wants us to use a midpoint Riemann sum, actually that's purple worthy, with 3 subintervals, and the goal is to approximate. And again, using correct units. So we can explain that first. Well, velocity is a derivative itself. Velocity is the derivative of position. It's the change in position over time, over a small period of time. So if we add up all of these small changes, that's what an integral does, it adds stuff up. If we add up all of these small changes over time, then we get the total change in position. Does that make sense? We're adding up a bunch of small changes in position over time, aka velocities, and over a long time interval, we end up getting the total change in position. So this is the total change in position, and specifically from those time intervals. So specifically from t equals, I guess we can say over the time period 10 to 70. So from 10 seconds to 70 seconds, we're finding how much the position changed because we're adding up these velocities. You might remember that velocity is the derivative of position, and acceleration is the derivative of velocity. So they want us to use a midpoint Riemann sum with 3 subintervals of equal length. So it makes sense they gave us so many spots here. So if we want to go from 10 to 70 in 3 subintervals, we're going to split it up here, and we're going to split it up, Wait, how are we supposed to do that? 3 subintervals. Am I missing something here? Ah, got it. Yeah, okay. So these should kind of be like on the 10 and on the 70. Okay. Yeah, that was freaking me out for a minute. So it's from 10 to 30, from 30 to 50, and from 50 to 70. Now, because we're making midpoint rectangles, yes, they're all going to be a width of 20. But what is the height going to be for these rectangles? Well, that's where the phrase midpoint comes in. So the way that we use the midpoint is we take the height from the midpoint of the interval. So that's 22, and on 30 to 50 interval, that's 35, and on 50 to 70 interval, that's 44. So we're kind of saying from 10 to 30, the rocket is going about 22 miles or feet per second. So we're just, multiplying that. Even though it's fluctuating and increasing during that time, we're using the midpoint to approximate this. So I don't know, let's write it over here, I guess. Integral from 10 to 70 of v of t dt is approximately, I don't think you get points off for saying equals rather than approximately, but it's just safer to put approximately because we are not sure about this being completely accurate. So we can factor out the 20 in time for all of the intervals because they all have the same width, and then we can basically just add up these midpoints. 22 plus 35 plus 44. Okay, so let's see what that is. 57 and 44. That's going to give us 101. Cool. Times 20. So we're going to have 2020. 2020 vision. To approximately 2,020 feet. Right? Because if we take a velocity, which is feet per second, and multiply it by a time, which is seconds, that cancels the seconds and we end up with feet. Okay, rocket B. Oh, we got some competition. Look out, Elon. Rocket B is launched upward with an acceleration of a of t equals 3 over square root t plus 1 feet per second squared. Per second is just per second squared. At time t equals 0, the initial height of the rocket is 0 feet. That makes sense. The rocket takes off from the ground. None of this alien technology. And the initial velocity is 2 feet per second. I still don't really understand that, but okay. Which of the 2 rockets is traveling faster at time t equals 80? Ooh. Which is traveling faster at time t equals 80? So we know how fast rocket A is going at time t equals 80. So we can just kind of say like VA of 80 is 49 feet per second. But in order to figure out how fast rocket B is going, we have to use the fundamental theorem of calculus with this acceleration to get our velocity. So if we take the integral of acceleration from A to B, what does that give us? That gives us V of B minus V of A. So it gives us the overall change in velocity. And we know that the initial velocity is 2 feet per second. So the integral from 0 to 80 seconds, which is the overall change in velocity, is going to take us to whatever the velocity at 80 is minus 2. It's going to represent the total change. So we have to take this integral. Let's rewrite the integral maybe as 3 times, t plus 1 to the negative 1/2. And we'll just work on that a little bit take this integral with the power rule. Raise the power by 1. It's not really a u sub. You can u sub it, but the du is just dt, so you're really not subbing that much out. If this were like more complicated on the inside, yeah, we'd have to do some kind of a u sub thing. Raise the power by 1. So we have t plus 1, oops, to the 1/2 now. And divide by the new power. So divide by 1/2, that's the same as multiplying by 2. So let's call that 6. T plus 1 to the 1/2 from 0 to 80. 80 is a nice number to use for this. If I plug in 80, I get 81. 1/2 power just means square root, right? So I can leave it like that and you're comfortable that it means square root. Plug in a 0, and that just gives us 6 times 9 minus 6 times 1. So basically like 6 times 8, 48. Now, here's the part that's going to trick so many people. It's very tempting to say, oh, I got the integral, it's 48. That's less than 49. Let's go, we're done. Nope. Nope, 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 nope. This is equal to v of b minus v of a. 48 is equal to the final velocity minus the initial velocity, because 48 was the integral, so 48 was the change in velocity. Okay. So since it changed 48 feet per second and it started at 2, that means the final velocity is 50. And so just like that, just by missing that, you can easily say that rocket A is going faster. But in fact, rocket B is bigger than rocket A's velocity at t equals 80. And I mean, we explained our reasoning, we gave all this integration. Using the fundamental theorem of calculus, setting that up properly, and using the initial condition is basically the explanation. Because I don't have to explain why 49 is is less than 50. That's a different class. Okay, so what kind of skills here? Just some good understanding about position, velocity, acceleration. So like particle motion relationships. It's a realistic problem with the rocket. So it's kind of easy to imagine that the rocket is increasing in velocity when it launches. I mean, most people know that happens. And a little bit of knowledge of how to set up these Riemann sums. They will ask you these occasionally, probably once per exam. Like, you should kind of anticipate one question having you do an approximation, whether it be a trapezoid, whether it be a midpoint Riemann, or a left hand or a right hand. Some kind of approximation is likely to show up in the free response. And then also, it can one or two of those questions can be sprinkled into the multiple choice portion of the exam as well. I'll say it every time. Units of measure are so important. You need to have units. That's a crappy thing to miss a point for. So if you don't have units on your stuff, I don't think it said units for this, but just on everything. If you're in physics already, you're probably used to doing that. But if you're not in physics and you want to make sure you're not losing points for something silly like units, just get in the habit of putting it every single time, even if you're overusing them. You don't necessarily have to do it within your calculations. That's more of a strict science, physics kind of thing, or chemistry. But, at least put them at the end and make sure you're keeping track of the units. Again, I don't want you to miss 2 or 3 points total because you didn't put units. It's such an easy thing to indicate, and you don't need to do any calculations, or really you don't need to give that much reasoning. So, yeah, that's enough blab out of me. I'll catch you guys next time in the void.